In this video, we're going to talk about something that we left incomplete yesterday, which is the idea of a tangent vector to a parameterized curve and a tangent line to a parameterized curve. And just as a quick reminder, parameterized curve is a term that's used interchangeably with a vector-valued function. When you graph a vector-valued function, a curve is formed in 2- or 3-dimensional space, and that curve is called parameterized because the locations are in terms of the output of a function, where the input is called the parameter. T is called the parameter. What we're going to need to do is calculate the so-called tangent vector, the unit tangent vector, the unit normal vector, and the unit binormal vector for a parameterized curve. And we're going to want to find a parameterized line tangent to a parameterized curve. So yesterday we studied in some detail this case of an object moving along a circular path. For example, an object that is attached to a string being spun in a circle. Now suppose that all of a sudden the string breaks. When the string breaks, the object is going to fly off in a trajectory that resembles a straight line.
Ivan Shikan from Belarus tried to knock him off top spot, but this effort would only be good enough for the silver medal.
On planet Earth, you might have to worry about things like drag and things like gravity, but if you were in outer space, for example, then the object would travel in a straight line for quite some time because of the laws of motion. If there isn't an external force acting on the object, then it will continue to travel along an unchanging direction at a constant speed for eternity until something comes in to change the object's velocity. So the string breaks and the object flies off on a straight line, and the question is, what line does the object fly along? And that's where the velocity vector comes in. If the object's position at any given time is given by r of t, and the object breaks free from the track of its movement at time t equals a, the force acting on the object vanishes and now it's just moving in a straight line, then the object's trajectory, the direction in which it's moving, is exact match to the velocity vector at that time. We saw yesterday several examples of the fact that the velocity vector, if you drew it on the graph of the path of motion, was tangent to the path of motion. And we saw in the cubic example as well, the tangent vector, velocity vector was tangent. And so this velocity vector at time t equals a is also sometimes referred to as the tangent vector, to honor and to capture this graphical fact that r prime, the velocity, is always tangent to the path of movement. Now also yesterday we took that tangent vector and we asked ourselves the question, okay, what if that vector was extended infinitely into a line? For example, what if the object were moving in space, and when it was launched from the string, it just continued to move in a straight line forevermore? What line would it be moving along? The line tangent to a parameterized curve contains the tangent vector as its direction vector, the tangent vector being equal to the output of velocity at the given time. Let's just call it A. Now, in order for a line to be tangent to a curve, it has to be attached to the curve. They have to share a point in common. So the point contained on the line that we'll use for our parameterized line formula will be equal to the point on the curve at that time, the position of the object at the time of launch, which will be equal to the output of the original function with no primes, the original position function at time t equals a. So based on that, if someone asked us for a formula for the tangent line to a parameterized curve at a given time, then we could find that formula by saying, okay, let's take our direction vector, let's scale it by the parameter t, and let's add the position vector so that our line is attached to the curve at that point. But there is an issue that can arise with this formula. And that's that the parameter t in this formula may not be referring to exactly the same time as the parameter t in the formula for r. T equals 0 in this formula for L of t refers to the moment when the object was released from the track, refers to the moment when the string was broken. Whereas t equals 0 in the formula for r of t refers to the initial time when the object basically started moving, which is generally speaking bad form. You shouldn't have the same variable t referring to two different quantities in the same problem. You shouldn't have one time variable whose 0 point occurred when the object was launched and have another variable also called t whose 0 point was the moment when the object started moving. So here's the better formula so that the values of t are consistent and have the same meaning, r prime of a times, and here's the adjustment that we'll make. Instead of scaling by the parameter t, I'm going to scale by the parameter t minus a. Now, t has the same meaning for both functions. For both functions, t equals 0 is when the object started moving, and t equals a is the time when the object was launched. So let's do a quick three-dimensional example. We have the parameterized curve where x and y are given by cosine and sine. So x and y are behaving in such a fashion that the object is moving horizontally in a circle. However, the z component is an exact match to the time. So as time goes on, the object is moving in a circle, but the height of the object is steadily increasing. Can you imagine what kind of path is formed when the x and y are spinning around in a circle, but the height of the object steadily increases? We get a graph that in many ways resembles a spiral staircase. The x and the y values are spinning in a circle, but simultaneously the z value is climbing. And so we get a spiral staircase shaped motion, which in formal terms is called a helix, a single helix. Now, when t is equal to pi over 2, cosine is 0, sine is 1, and the height is pi over 2. So I'm going to indicate that the time pi over 2, at that time the object is located in this position right over the positive y-axis. The position at pi over 2 is right here. Someone says, okay, please find the tangent vector at this time. Now, you've already done this kind of calculation. It's just that the language here has slightly changed. The tangent vector at this time is exactly the same as the velocity vector at that time. So the first thing that we need to do is find a general formula for the derivative of r. Negative sine, cosine, and 1. Only when that has been done are you free to plug in the specific time that they're interested in, pi over 2. And so pi over 2, we get negative 1, so it's pointing toward the negative x direction. It's not pointing at all in the y direction, and it's pointing slightly upward in the z direction, which matches what we might expect based on the graph of the helix. This tangent vector at that time will be pointed straight back with a slight upward tilt to capture the fact that the object is moving upward. Now someone says, I'm interested not just in the tangent vector, but I'm interested in the entire tangent line. What if you took that tangent vector and extended it to a full line? Now if you want to extend the tangent vector into a full line, all that you have to do is fill in the blanks of the general formula. Now we found the tangent vector, negative 1, 0, 1. So that will basically act as the slope of our line. And now I'm going to scale this direction vector, but not just by the time t. If I scale it by the time t, then that will lead to a discrepancy in the meaning of the variable t between our movement curve and our tangent line. Instead, I'm going to scale by the parameter minus pi over 2. Then, over to the side, I've written down the object position at the time of launch. I'm going to write down the position at time pi over 2, 0, 1, pi over 2. You can simplify this if you're so inclined, but you don't have to. In part C, we get to see the advantage of taking the effort to make sure that our definition of time is consistent in all areas of the problem. Suppose that the output of r of t represented the position of an object moving along a track, and suddenly something happens that causes that object to be released from the track. Once it's released from its track, it flies, at least for a short time, in a straight line. So if it's released from the track after about 1.5 seconds, where is the object, roughly speaking, at 2 seconds? Roughly speaking, half a second after launch. If we want to find out where the object is at approximately t equals 2 seconds, half a second after launch, then what we can do is we can take that time of 2 units and we can plug it into the formula that we found for the parameterized line. Negative 1, 0, 1, 2 take away pi over 2, plus 0, 1, pi over 2. So negative 1 times this scalar will flip the signs. 0 will kill this scalar, and then I have 1 from the other vector. And then I have 2 minus pi over half, plus pi over half. But that can be simplified simply to 2. And so I'm left with this number. Now let's go to our picture and let's check and see if this position makes sense based on our sketch. Which makes sense actually based on what we calculated. If the object is launched at this blue position along the helix, moving along this purple tangent vector for at least a short time, then it does look like we will still have this positive y component. The object is moving to the back, so it begins to have a negative x component, and it keeps climbing upward, at least for a short time, so it makes sense that the z component has gone slightly upward. So with that is the application of the tangent line to find the position of an object after it's been launched off of a curve. Just be careful to define the parameterization with this adjustment on the parameter so that the significance and meaning of the variable t is the same for all the different curves in your problem. The same t value corresponds to the same time for all your functions. In mathematics, we have sort of a sacred basic coordinate system. The origin is located at the point 0, 0, 0. X points towards us, y points to the right, and z points upward. But in real life, there is no sacred scripture telling you where the origin has to be or how the coordinates have to be oriented. In a real life problem, you're going to position the origin at whatever location is convenient for you, depending on what you're working on. And your x and y and z coordinates, those axes will point in whatever direction is convenient for you, depending on what situation you're working with. In fact, oftentimes, it can be useful to have a coordinate system that actually changes as your object moves. For example, you see this quite a bit in computer software when you're dealing with 3D models. Everyone's favorite 3D modeling software, Blender, for example, will actually change the orientation of the x, y, and z axes when you rotate the object that you're working with. Here I am in Blender with our beloved default cube, and by default the cube is positioned at the origin. And the origin and the coordinate system are indicated by, first of all, this orange dot. That is where the origin is located. And then we have this red line, which is indicating the x-axis, and the green line, which is indicating the y-axis, with the understanding that the z-axis is coming up perpendicular to both of those, but it's not shown for visual clarity. Now, by default, when you go to scale this object, when you go to stretch it in a certain direction, suppose that I want to stretch it in the y direction. Then I can hit S and I can hit X, and it will produce this red line to indicate, this bright red line to indicate that now we're stretching the object along the x-axis. However, if I rotate the object a little bit, let's rotate it this way, and I go to scale it, I have the option to scale it along the true global x-axis, but if I hit X one more time, it will give me an alternative x-axis which rotated together with the object. When I rotated the cube, a local understanding of the x-axis rotated with the cube, and now I can scale along either the global x, or I can scale along a local version of the x-axis. We saw it in the 3D modeling software Blender. We can also see it in lots of different game engines. For example, this happens in Unity as well. We have this object in the sample scene, and if I click on it, I can move it along any of these directions. Now already the axes for this scene, for the objects in this scene, are a little bit different from the normal. Because red, the positive x direction, is currently facing away from us, y is pointing straight up, and z is pointing over here to our left. Now if we take this object and we rotate it, let's go way out there. Yeah. Now you can see it more clearly. The axes have rotated together with the object. So now, independent of a global coordinate system, which is indicated here in the upper right, there is now a local coordinate system which applies specifically to this object, where now y and z are on a slant matching the slant of the object itself. Now in the specific case of a moving object, there is a commonplace way to change the position of the origin and to change the orientation of the coordinate axes. If your object is moving along the graph of a vector-valued function r of t, then your general choice is to set the origin at any given time equal to the object's position. In other words, you move the origin with the object so that the object's position is always at the origin. Likewise, for an object moving along a vector-valued function, it's common to replace the standard basis vectors I, which points in the positive x direction, j, which points in the positive y direction, and k, which points in the positive z direction. It's common to replace those with three vectors that are more closely related to the object's actual movement in space. Now, the idea is to replace I, j, and k with three vectors that have a similar relationship as I, j, k. Notice that all three vectors have length 1. So they're all what we call unit vectors. Notice that all three of these vectors are also orthogonal to one another. In other words, I dot j is equal to 0, they're perpendicular, j is perp to k, and I is perpendicular to k as well. So when we replace I, j, k with a different coordinate system, we also want the alternative coordinate system to create this sort of corner, this right-angled corner. And so we replace the standard basis vectors with three orthogonal length 1 vectors, and these vectors are called the unit tangent vector, the unit normal vector, and the unit binormal vector. The unit tangent vector is basically replacing I. The unit normal vector is basically replacing j and pointing in the new local y direction. And binormal is replacing the z direction, replacing the vector k. So let's go through some of the formulas that are used to find this unit tangent vector, this unit normal vector, and this unit binormal vector. Now, the tangent vector was what we called r prime at whatever time you were interested in. The velocity vector with the time t equals a plugged in. Now, that's the tangent vector, but for this coordinate system, we want a vector of length 1 to match the fact that the vector I, pointing in the x direction, is taken to have length 1. Now, if you want to take a vector and find a unit vector pointing in the same direction, do you remember how we did that to take a vector and turn it into a unit vector? All you have to do is take that and divide it by its length. Take the tangent vector, divide the length, and lo and behold, you have the unit tangent vector. Now, this quantity is given very specific notation. This is called capital T. Capital T with a vector over it is used for the unit tangent vector. This is case sensitive, just like your passwords, right? Little t is the parameter, it's the input variable. Capital T is referring to the tangent vector, so totally different. And in fact, if you read our textbook, you're going to see this somewhat spooky expression, capital T with t plugged in. Capital T with t plugged in is a reference to a vector-valued function which outputs the tangent vector at any given time. So when I'm reviewing your work, I don't want to see people playing fast and loose with the cases here. You're going to have to be very clear about what is a lowercase t and what is a capital T. I know some of you out there write all your letters in all caps all the time, and usually you can get away with that, but not here. Here, lowercase t and capital T are used in exactly the same problem and mean very different things. Alright, the formula for the unit tangent vector, very simple. Find the regular tangent vector and then divide by the length to make it a unit vector. That's how we find a local version of the coordinate x. Next up is the local version of the coordinate y, and this is called the unit normal vector. Now the unit normal vector has to be calculated after you find the unit tangent vector. You need to find a formula that will output the unit tangent vector at any time. So first find the velocity vector, then find the speed, and divide the velocity at any given time by the speed at any given time. First, you need this. Note t equals a has not been plugged in at all yet. Okay, so the first thing that you need to do is you need to get a general formula that will output the unit tangent vector at any given time. Once you have done that, you can find the unit normal vector by taking the derivative of the unit tangent vector. And dividing that by its length. The unit normal vector is called n, just as the tangent vector was called t. Once you have found that quantity, then you can go ahead and plug in your given t value. Unit tangent vector, take the derivative of position, divide by length. Unit normal vector, take the derivative of the unit tangent vector and divide by length. For r of t equals cosine 2t, sine 2t, and t. Let's find the unit tangent and the unit normal vector at t equals 0. Now again, whenever I'm dealing with derivatives, I save plugging in until the very, very last step. If you plug in too early, it will completely mess up all your derivatives after you plug that number in. So don't plug t equals 0 into anything until you have calculated all the derivatives that you need for your problem. Now the first thing that I'm going to work on is the unit tangent vector. And in order to get the unit tangent vector, I need velocity, the regular tangent vector. So I get the derivative of cos 2t, which is negative 2 sine 2t, the derivative of sine 2t, which is 2 cos 2t, and the derivative of t, which is 1. In order to make this a unit vector, I need to find the speed at any given time. So I'm going to go in and take the square root of the x component, the square root of the y component on the square root of the z component, and I'm going to work on simplifying that. In this section, Pythagorean identity is going to be your best friend. Because when you see number times sine squared, the same number times cosine squared, Pythagorean identity says that sine squared plus cos squared is equal to 1. 4 times 1 would then be equal to 4. And combining that with the 1 from the z component, we get a constant speed of square root 5 units. As a result, what is the unit tangent vector at any given time? The unit tangent vector at any given time, we can take r prime of t and divide it one component at a time by the speed that we calculated. So negative 2 over root 5 sine 2t positive 2 over root 5 cos 2t, and then if we divide the z component, 1 over root 5 for the z component. This is a formula that can be used to produce the unit tangent vector at any given time. For example, we could plug in t equals 0 to find the unit tangent vector at that time. But I'm not going to do that yet because I still have additional work to do with the derivatives. The next thing that I need to do is I need to find the unit normal vector, which means that I'm going to need to, in the process of that, find the derivative of the t of t that I got in my previous calculation. So take your unit tangent vector, find its derivative. If I find its derivative, now because of chain rule, once again, another 2 pops out, and I get negative 4 over root 5 cos 2t. I get negative 4 over root 5 sine 2t. And 1 over root 5 is constant, so its derivative is 0. The derivative of the unit tangent vector may not be a unit vector anymore. So let's go ahead and find the length of t prime and then divide out that length to make it a unit vector. So let's take the square root of the x component squared y component squared, and since the z component is just 0, it won't contribute anything to this problem. Let's algebraically simplify this. 4 squared is 16 divided by 5. The other, negative 4 squared over root 5, will also become 16 over 5. And then we have cos squared of 2t plus sine squared of 2t, which is simply 1. Once again, we're using that Pythagorean identity. So this simplifies to positive 4 over root 5. That is the length of this derivative of tangent vector at any given time. So let's go through and let's divide the derivative of the unit tangent vector by its length. So this 4 over root 5 divided by another 4 over root 5 will just go to 1, and then the minus sign is there. Negative cos 2t. Negative 4 over root 5 divided by 4 over root 5 also goes to 1, so we had left with negative sine 2t. And then 0 divided by anything is still 0. This is the formula for the unit normal vector at any given time. And finally, it is completely safe to go through and plug in t equals 0 to find the specific unit tangent and unit normal vectors at the given time. Scrolling back up, we have t of t is equal to sine cos. So when t is 0, the sine will zero out and the cos will become 1. So we'll have 0, 2 over root 5, and 1 over root 5. Finally, the unit normal at time t equals 0 can be found by plugging 0 into the general formula that we found above. So sine zeroes out, cosine produces 1, and we get minus 1, 0, 0. Okay, now the last quantity that we need to find when we're trying to fill out a local changed coordinate system, a new frame of reference, we need to find the vector that's going to take the place of the k vector, the one pointing in the positive z direction. Now, once you've found the unit tangent vector and once you've found the unit normal vector, in some sense the hard work is over. And the unit binormal vector is, in my opinion, one of the easier ones to calculate, because you actually can find this without using any derivatives. The idea with the unit binormal vector is to mimic the fact that if you take the standard basis vectors I and j and you find their cross product, then k, the z vector, ends up being the result. So for the unit binormal vector, which is called b, correspondingly b for binormal, you can get that by taking the equivalent of I, which is the unit tangent vector, and you can cross that with the equivalent of j, the unit normal vector. Of course, in order to do this, you already need to have found the unit tangent and unit normal vectors. So generally speaking, the process of finding these vectors, the order is very specific. The first thing that you need to do is find the unit tangent and the unit normal vector at that location. Then you can take their cross product and that will give you the unit binormal vector. Now just a note here. One of the nice things about the unit binormal vector is that it doesn't actually require you to take any derivatives. And that means that unlike the other two vectors, the unit binormal vector can be calculated after you plug in your given t value. So in order, what steps would I take to fill out a complete TNB frame of reference, tangent vector, normal vector, binormal vector? The first thing that you want to do is you want to find the velocity vector for your function. Then you want to find its speed. Then you want to find the unit tangent vector, which is velocity divided by speed. Then you're going to start working on the unit normal vector. So take the derivative of the unit tangent vector. Then find the speed of that. Then divide the unit tangent derivative by its length to get the unit normal. At this point, finally, all the derivatives have been calculated, which means you are now free to replace that variable t with the value of t that you have been given for your problem. So in step number 7, that's right, we're up to 7 already, you can go ahead and you can calculate t, the unit tangent vector, at the given t value. And you can calculate the unit normal vector at the given t value. And then you can finish the problem by taking the cross product of those two, t first and then n, to find the unit binormal vector. Just a warning, when you take the cross product of two vectors, order matters. just as x comes before y, t comes before n. Not necessarily in the alphabet, but in terms of the order of this cross product. At last, to see how the unit binormal vector can be calculated in a particular example, let's go back here to our helix-shaped friend cos 2t, sine 2t, and t, considering t equals 0. So, scrolling back up, our unit tangent vector at that time was 0, 2 over root 5, 1 over root 5. Our unit normal vector was negative 1, 0, 0. To find the unit binormal vector, I can take that unit tangent and that unit normal, and I can cross them using the good old-fashioned 3x3 matrix determinant formula. So 0, 2 over root 5, 1 over root 5, and then negative 1, 0, 0, specifically in that order. So looking at the x component, we have 2 over root 5 times 0 minus 1 over root 5 times 0. So both products are 0. Then for the second component, the prime diagonal has 0 times 0, and the anti-diagonal has negative 1 times 1 over root 5. And then looking at the k component, we have 0 times 0 minus negative 1 times 2 over root 5. All in total, our unit binormal vector at the time is 0, then 1, 2, 3, 3 negative signs, and then 2 negative signs, so plus 2 over root 5. And you can go back and you can confirm that all the vectors that we found, the unit binormal vector, the unit normal vector, and the unit tangent vector, all have a length of 1 because they're unit vectors, and they're all orthogonal to one another. So t dot n is 0, t dot b is 0, and n dot b is also 0. Now here is a sketch of the path that is traversed by the object. It's a helix, still once again a helix, because the cos and sine and the x and y components are creating a circular motion, and the t and the z component is creating an increase in height over time. Now at time t equals 0, the object's location is indicated by this white dot. 1 unit in the positive x direction with no units of movement in the y or z direction. The unit tangent vector points in the positive y and positive z directions. So it's pointing to the right with a slight upward tilt. Tangent to the direction of movement, truly tangent. All right, now the unit normal vector. The unit normal vector was negative 1 in the x direction and 0 for y and z. So this is pointing straight back at a right angle to Tn, straight back toward the origin. Now meanwhile, b of 0 is not pointing at all in the x direction. It's tilted slightly back in the y direction, and it has a pretty robust z component. So finally, b0 is tilted back this way. Forming a right angle with both n and in the front with t. Now, as your object continues to move along the curve, the n and the t and the b will adjust themselves to match the object's movement. For example, over here, at this location, Tn will be pointing in the negative x direction. The unit normal will still be pointing inward toward the direction of acceleration. And b0 will still be such that it's at a right angle with both of those two. And so you will see this coordinate system, this frame of reference, move as the object moves. Okay, so to sum up what we did today, the first thing that we did is we looked at the regular tangent vector to a parameterized curve, which is equivalent to its velocity vector. If you extend that velocity vector into a full line, you get what's called the tangent line. Then we looked at a replacement for the x and y and z coordinates, a replacement for the vectors I, j, k, called the unit tangent, the unit normal, and the unit binormal vector. To find the unit tangent vector, take the regular tangent vector and divide by its length. To find the unit normal vector, take the derivative of the unit tangent vector and divide by its length. And then to find the unit binormal vector, cross the unit tangent with the unit normal. And that will get you 3 unit vectors, all of which are orthogonal to one another, mimicking the behavior of I, j, and k, the standard basis vectors in 3 dimensions.